Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element Praseodymium. You may think this element has the longest name, but no, there are two others, Protactinium and Darmstadtium, that are equally long, and one other element, Rutherfordium, that beats it by one letter. I have a sample of Praseodymium here in this vial. Let's take a look at that right there. I know it might be kind of hard for you to see, so let's go back to our presentation because I have a better scan of it here. So you can see that it's kind of a shiny and silvery metal, and we're going to be looking at this a lot closer. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called Earth.Elements, which I encourage you to go out and pick up. Check out his fantastic website, periodictable.com. Praseodymium is the 59th element in the periodic table. Its atomic number is 59 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. In 1751, Axel Cronstedt discovered a mineral from a mine in Basnäs, Sweden. 30 years later, 15-year-old Wilhelm Hisinger, whose family owned that mine, sent some to Carl Scheele to analyze, but Scheele failed to find any new elements. Another 22 years pass, and in 1803, Berzelius and Hisinger examined it themselves and isolated a new oxide that they called Syria after the newly discovered asteroid Ceres. Move forward another 36 years, and Swedish surgeon and chemist Carl Gustaf Mosander, who lived, by the way, in Berzelius's house, separated out two oxides from Syria, which he called lanthana, which was lanthanum oxide, and didymium. Turns out that didymium is not a pure element, but rather a mixture of rare earth elements. It was not until 1885 that Karl Auer von Welsbach separated didymium into praseodymium and the next element in this series, neodymium. A pure sample of praseodymium metal itself was first produced in 1931, but for the life of me, I can't seem to find out who purified the metal. One source of the earlier rare earth elements is the mineral monazite. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as substituting elements. It's usually found in the form of a sand with other constituents. India, Madagascar, and South Africa have large deposits of monazite sands. Another source of praseodymium is the mineral bastnäsite, which is a carbonate fluoride with lanthanum, cerium, praseodymium, or yttrium as substituting elements. Both monazite and bastnäsite are mined for praseodymium and other rare earth elements. Rare earth production, including praseodymium, has grown exponentially since the 1950s, doubling about every 15 years. Early on, production was small and scattered. The U.S. got into the game around 1965. China started producing 20 years later in 1985 and has since dominated production. Let's expand and magnify production since 1994. Notice that the U.S., the green areas, and Russia, the smaller magenta areas, turned down production and leave the game in 2005, unable to compete with China. However, in 2010, China drastically cuts exports, coaxing the U.S., Myanmar, and Australia to start or restart production. China is still the 800-pound gorilla, but now there are other sources as well. The only rare earth mining and processing facility in the United States is the Mountain Pass Mine, 53 miles southwest of Las Vegas. The mine supplies almost 15% of the world's rare earth production. While this mine specializes in praseodymium and neodymium, they also extract lanthanum and cerium. Refining rare earth elements is a multi-step process. For monazite, it starts with the sand, and after 12 steps produces rare earths, including praseodymium. Separating the rare earths from each other is also a long and arduous process. The steps here can also yield uranium and thorium, which is often another component of monazite. The name of the element is derived from the Greek praseos, meaning green, and didymo, meaning twin, hence green twin or praseodymium. Why green? Here we see some praseodymium salts, praseodymium nitrate, sulfate, and chloride. Green indeed. Note that the dymium part comes from the didymium that was separated by Mosander into praseodymium and neodymium. Neodymium translates to new twin, our next element in this series. Praseodymium belongs to a row of elements known as the rare earth metals, or lanthanides, since lanthanum is the first element in this periodic table row. Praseodymium is the third element of this series. Technically, both scandium and yttrium are also included in this group, since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium, but if we displayed the table in this fashion, it becomes too long and unwieldy. As with most elements, the price of praseodymium varies widely with purity and the quantity you buy. 99% pure praseodymium goes for about $103 per kilogram, fairly cheap given its apparent rarity. The element praseodymium is fairly uncommon in the universe, coming in as the 56th most abundant element in the universe by mass, only 2 parts per billion. At 65th, praseodymium is extremely rare in the Sun too, only 1 part per billion. It's also 65th most common element in meteorites, also about 1 part per billion. Surprisingly common compared to everywhere else, in the crust of the Earth, it's the 37th most common element, almost 9 parts per million, about the same as lead. Praseodymium is the 68th most abundant element in the oceans, virtually non-existent at 0.6 parts per trillion. And lastly, and not surprisingly, there is no praseodymium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Praseodymium is here. I understand this looks complicated, but let's look at just praseodymium a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of praseodymium created by various processes. The vast majority of praseodymium present today is believed to be produced by dying low-mass stars, the magenta area. A tiny amount is produced in supernovae, the yellow area, and a very small portion, that green sliver on the top, is produced in neutron star mergers. Note, the praseodymium produced by dying low-mass stars, the magenta area, doesn't get started until a bit later in the history of the universe. That's because low-mass stars exhaust their nuclear fuel much more slowly, and they last a long time before they start dying. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 59 protons for praseodymium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 39 known isotopes of praseodymium, making it, along with barium and mercury, one of the elements with the most isotopes. Of these 39, there is only one stable non-radioactive isotope, praseodymium 141. Praseodymium is therefore a monoisotopic element. There are 23 of those, by the way. The stable praseodymium 141 isotope obviously makes up all of the naturally occurring praseodymium in the universe. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of praseodymium occupy the same place in the periodic table. Of the radioactive isotopes of praseodymium, these 6 are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest lived praseodymium isotope is praseodymium 143. It has a half-life of only 13.57 days. Even the longest lived radioactive isotope has a very short half-life, which is why, unless these radioisotopes are made in reactors or atomic bomb blasts, none exists in nature. It's all decayed away. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. You'll see why I chose 1,024 atoms. Hint, it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms. And so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice that there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Praseodymium has a medium density at 6.64 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up a couple more densities for you here. You can see that praseodymium is a bit less dense than iron. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, praseodymium's density is 6.64 grams per cubic centimeter, the magenta circle between titanium and iron. Praseodymium has a fairly low melting point at 931 degrees Celsius, which is about 1,340 degrees Fahrenheit. It boils at a fairly high 3,290 degrees Celsius, or almost 6,000 degrees Fahrenheit. That's a full 2,359 degrees C above its melting point. Quite a difference. If we compare the size of the praseodymium atom to that of hydrogen, we'd see something like this. The praseodymium atom is almost 5 times the size of hydrogen. Those 2 outer electrons are held fairly loosely. By the way, A picometer is a trillionth of a meter. Atoms are very small. Here are atom sizes sorted from largest, cesium, on the left, to smallest, helium, on the right. Praseodymium has the fourth largest sized atom of all the elements and is the largest of the rare earth elements. Praseodymium is a soft element, coming in at only 1.41 on Mohs scale of hardness. You could easily scratch praseodymium with your fingernail, which has a hardness of around 2.5. Here's a chart of element hardness from the hardest, boron, on the left, to the softest, cesium, on the right. Praseodymium is the 11th softest element, not much harder than the softest element, cesium. Praseodymium is very malleable and ductile. Praseodymium has the 15th lowest rate of thermal expansion, only about 7 parts per million per degree C. This means that if you had a 1 meter long bar of praseodymium and you heated it by 1 degree Celsius, it would get longer by only 7 millionths of a meter, or about 1/10 of a hair width. Aluminum expands 3.5 times as much. Here's the periodic table of the spectra. Praseodymium has a very complicated set of emission lines all across the spectrum. Let's take a look at a few applications of this rare earth element. A major use of praseodymium is in making metal alloys. Pure magnesium metal is not normally used in structural pieces due to its lack of strength, but alloy magnesium with praseodymium and it becomes stronger, useful in cars and aircraft engines. I already mentioned that Carl Gustav Mosander thought he discovered an element called didymium. Remember that didymium turned out to be a combination of both praseodymium and neodymium. Sir William Crookes discovered that when these two elements were added to glass, they tinted the clear glass with a pinkish color. This glass, called didymium glass, has some unique light-blocking capabilities. Here's the absorption curve of didymium glass. I know some of you may not be familiar with the color of light associated with those wavelengths along the x-axis. Let me put up the spectrum behind the graph so you can see the colors. Ultraviolet is to the left of visible light, and infrared is to the right. The didymium glass blocks yellow light quite well. Specifically, it blocks the light given off by excited sodium atoms almost completely. Notice that the percent of yellow light transmitted by this filter is virtually 0% of the yellow light. Although you can see it partially in this graph, the glass also blocks infrared light quite effectively. Why is this important and useful? When glassblowers are doing their work, the glass working flame hits the heated glass, which contains sodium. It glows in a blindingly bright yellow light. It's hard for the glassblower to see what they're doing. If the glassblower wears didymium glasses, the yellow light is blocked, and the melted glass is much easier to see and work on. In addition, blocking infrared also protects the glassblower's eyes. Because of the strange color absorption curve of didymium glass, you get the odd effect that it looks different under different illumination. Here, we see the same 2-inch square of didymium glass under incandescent light on the left and fluorescent light on the right. This is due to the differences in the spectrum of the light passing through the filters. Incandescent light on the left and fluorescent light on the right are completely different. The light passing through the filters, combining with the absorption spectrum of the didymium glass seen a couple slides ago, creates this effect. Let's take a look at another example. Here is the same light bulb with a didymium glass envelope under fluorescent light on the left and incandescent light on the right. A stunning difference. This is the same piece of glass. Notice the shape of the breaks and cracks. We'll see this yet again in a few slides. I don't know if this is legit or not, but here's a light bulb for reptile terrariums that claims to be full spectrum, which is supposedly better for your cold-blooded pet. They do this with didymium glass, though the box says neodymium. I think we need more scientists in the marketing department. These fellows are the Moser brothers, Karl, Richard, Leo, and Gustav, whose father, Ludwig Moser, founded the famous Moser Glassworks, still producing some of the most beautiful glass in the world. One of the brothers, Leo, took over the glassworks and made many innovations, one of which was to introduce the use of rare earth oxides as glass colorants. He investigated the use of praseodymium in glass coloration in the late 1920s. Here's one of Moser Glassworks' beautiful pieces. This one is made from didymium glass. Here's a Moser didymium goblet under fluorescent and incandescent light. Because of this color change, this glass is often mistakenly called alexandrite, which is a rare gem that also changes color under different lighting. But this is not because of rare earths. Rather, it's because of the light-absorbing qualities of a different element, chromium. Leo Moser not only used didymium for its purple-pink coloration, but also praseodymium by itself. Living up to its name, green twin, praseodymium alone colors glass a beautiful green. The result was given the name prasemit. However, a similar color could be achieved with colorants costing only a minute fraction of what praseodymium cost in the late 1920s. So, the color was not popular and very few pieces were made. You're probably familiar with those super strong magnets, often called rare earth or neodymium magnets. Well, it turns out that praseodymium and neodymium are so similar that for magnets, they're practically identical. So manufacturers of neodymium magnets don't bother to separate the two elements usually. Most neodymium magnets are actually 25 to 35% praseodymium, so they really should be called didymium magnets. Peridot is a valuable type of semi-precious gemstone. What you see here is cheap cubic zirconia colored to look like peridot using a bit of praseodymium. Cubic zirconia comes close to diamond in light-bending power and color-producing dispersion. Here I have a piece of clear cubic zirconia, which is a really good diamond simulant, but obviously much cheaper than diamond, or else I would never have been able to afford two of these 50-carat gems that I purchased for about, $20. It's a good diamond simulant, but far softer than diamond, only 8 to 8.5 on Mohs scale of hardness compared to diamond's hardness of 10. What makes it interesting to me is that praseodymium is used to impart just the right fake shade of yellow-green to cubic zirconia to make it look like peridot. The first enduring commercial use of purified praseodymium, which continues today, is in the form of a yellow-orange stain for ceramics called praseodymium yellow. Carbon arc lamps use a mixture of rare earth elements, including praseodymium, to improve light quality. This type of lighting, especially as used by the motion picture industry for studio lighting and projection, consumed about 25% of the rare earth compounds produced until carbon arc lamps were phased out. The rare earths were placed in the core of the carbon rods and made them burn with a beautiful white-balanced light, perfect for film. You may have seen carbon arc light sources used in giant spotlights in front of store openings or movie premieres. This one's just a sad attempt to sell office supplies. No glamour there. Most carbon arc lamps have been replaced with short arc xenon tubes. These tubes last longer than the carbon rods, and there's no flames to worry about. About 4% of the alloy misch metal can be praseodymium. It also contains up to 50% cerium, 25 to 45% lanthanum, up to 15% neodymium, 6% other rare earth metals, and iron to hold it all together. And it gives it some strength too. It's very sparky stuff. Misch metal was invented by the inventor of the lantern mantle, Karl Auer von Welsbach, who realized that didymium was 2 or more elements. Misch metal is pyrophoric, which translates to fire-bearing. Pyrophoric solids ignite in the air when they're finely divided into a powder and elevated in temperature by friction. The oxidized metal left behind from the sparks form tiny crystallized spheres that, when magnified in an electron microscope, look like they came straight out of a science fiction film. Misch metal is used to make lighter flints, like you see on the right, and the spark-producing metal in torch strikers, like you see on the left. Another popular product with campers and survivalists are ferrocerium rods. Scraping them with a sharp edge results in a shower of very hot sparks capable of starting a fire. Let's look in slow motion at scraping a ferrocerium rod. The negative electrode, or cathode, of rechargeable nickel metal hydride batteries is a mixture of, well, metal hydrides, typically a rare earth misch metal hydride containing lanthanum, cerium, praseodymium, and neodymium. Turns out that the mixture of rare earths seems to work about as well as pure rare earths, and the misch metal mixture is much cheaper to produce. The next few applications are really geeky, so put on your propeller beanie and fasten your seatbelt. If you thought that magnets and heat had nothing to do with each other, you're going to love this one. There's actually something called the magnetocaloric effect. If you make an alloy with praseodymium and nickel in these proportions, you can use it to create an amazing effect. We'll start with a brick of this metal. Now we need a strong electromagnet. We take our alloy brick and place it between the pole pieces. When we switch on the magnetic field, the domains in the brick's alloy align with the field of the magnet. The net effect of this heats the brick. The hot brick now radiates away heat into the environment and cools back down. The magnetic domains are still aligned with the magnetic field. Now, if we shut off the magnet and remove the block, the domains in the alloy will once again randomize, but this makes the brick cooler. The process can be repeated over and over to achieve lower and lower temperatures. This effect was first observed in 1881 by German physicist Emil Gabriel Warburg. Our praseodymium alloy has such a strong magnetocaloric effect. Using this method has allowed scientists to approach within 1 millikelvin, or 1/1000th of a degree, of absolute zero. When light moves from a vacuum to a denser medium, like glass or water, it slows down. In a diamond, light slows by quite a bit. In a diamond, light moves only about 41% the speed it moves in a vacuum. That may seem a lot slower, but that's still 76,000 miles per second. Recently, physicists have been able to use a praseodymium-doped yttrium orthosilicate crystal seen in the center of this complicated apparatus diagram to slow light down to only a few hundred meters, not kilometers per second. Slower by a factor of 100,000 than when compared to a vacuum. This can be used in quantum computing. The explanation of the experiment is way beyond the scope of this program, but it's an interesting application. Praseodymium, when incorporated into fiber optics, can be used to amplify and boost signals on the fiber. This is called an O-band fiber amplifier, and it's praseodymium that makes it all work. For our final GeekFest application, this is the highest resolution atomic image ever captured. Each bright spot is an atom. Using a technique called electron tachography, the image shows a reconstruction of a praseodymium orthoscandate crystal, zoomed in 100 million times. Like the previous few applications, the methods used to make this image are beyond the scope of this presentation, but the paper is available online if you're interested. Your body does not use praseodymium, but probably still contains a few micrograms absorbed from the environment. Though there's no biological role in humans, it is used by certain types of extremophile bacteria, such as this methylacidophyllum fumariolicum. These were first found in 2007 in hot mud pools surrounding volcanic vents near Naples, Italy. This is a volcanic mud pot in Yellowstone National Park. The early lanthanide elements such as lanthanum, cerium, praseodymium, and neodymium are used by the bacteria to break up methane to feed the organism. How amazing that these evolved to use such elements as an essential part of their metabolism and in such an extreme environment. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about praseodymium. Magnetic cooling. Absolute zero beckons. Approach the limit. In the next program in this series, we'll examine another part of didymium, the new twin, neodymium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about praseodymium.